Okay, welcome back everyone. In this video, we're going to look at an example of applying F equals ma using centripetal force. And so this is actually number 56 on page 251. So I'm not going to write out the problem, but basically what we have is a pilot who's going in a vertical circle. And the reason that this is important is that now we have to think about the force of gravity. And so the pilot in his seat in the plane is undergoing this circular motion, and for part A we want to determine where the normal force is the greatest. And we have a couple of places to choose from. So what we should do is identify forces at each place and think about what's going on. So for example, at the bottom of the path, the force of gravity will be downwards and the normal force will be upwards. Now the end result is that these two forces need to make the pilot go in a circle, and so therefore the net force will be upwards, although it's probably best if we write that his centripetal acceleration will be upwards. Now at the top we have the force of gravity going downwards, and we also have the normal force going downwards, and the result of that is going to be a inwards centripetal acceleration. Notice that in both places this centripetal acceleration will point towards the center of the circle. So the question is, where is the normal force greater? Well, I think if you think about this and think about your experience like on a roller coaster, you might realize that when you're at the top you feel a little bit lighter, and when you're at the bottom you feel a little bit heavier. So if this was just a part of a roller coaster and you're going like this, you'd feel heavier at the bottom. Now the reason for this is that the normal force has to push you towards the center of the circle, and it has to overcome gravity. At the top of the circle, by contrast, the normal force is getting help from gravity because they point the same direction. And what we'll do in the second part of this is we'll actually calculate the normal force at each point. So in part B, we're going to find the normal force at both the top and the bottom. And so the strategy for solving problems like this is pretty simple. We say that the net force is equal to mass times centripetal acceleration. And then we also say that inwards, by definition, is going to be the positive direction. So no matter where we're at, if we're on the side over here, a force which points inwards is in the positive centripetal direction. So we're not necessarily talking about x and y, we're looking at radial, which is either you're pointing towards the center or you're pointing away. And this simplifies things. Okay, so let's look at the top. So at the top we have the normal force, which is pointing inwards, so it gets a positive sign, and we have gravity, which also points inwards, so it gets a positive sign, and so we can calculate the net force on the left side is normal force plus gravity, and on the right side is the result of that, the centripetal acceleration times the mass. And now we do have some numbers. We're given that the speed is 700 kilometers per hour, which if we do a conversion on this is 194 meters per second. I'll leave that conversion to you, but we basically divide by 3.6. Okay. And so what we can do here is use the fact that, first of all, let's bring mg over to the other side. And then let's also use the fact that centripetal acceleration is v squared over r. And I think that what we're given in this problem is that the radius is 2,000 meters of this circle. Okay? And now what you can see here is that the normal force is going to be a little bit less than mv squared over r because gravity is helping out, and this is at the top. Okay, so let's just label that, and so we can calculate that at the top here we have F normal. I don't know if we have a mass for the pilot, but what we can do is we can calculate v squared over r, and at the top that turns out to be about 194 meters per second squared over 2,000 meters, and then m, and then g. Okay, now I'm just doing this the way that the book does, so it's a little bit weird with the numbers. I'm going to write this is m times 18.8, and then I have m, and g is 9.8. Okay, and so what happens is we subtract these and we get about 0.93 times m times 9.8. Now the important thing here is that this turns into 0.93 mg. And if I knew the mass of the pilot, then I could plug that in and calculate exactly how many newtons of force we have. But this is in terms of mg, the pilot's weight. Okay, now let's look at the top. Now the difference at the let's look at the bottom. The difference at the bottom of the loop is that now gravity is hurting us. Gravity is pointing in the outwards direction. So it would look like this: F normal minus mg equals mac, or F normal equals mv squared over r, that's ac, plus mg. And so now this is m times 18.8, the same thing, plus 9.8, and if I factor g out of that, I'm going to get about 2.93 times mg. And so what this tells us is that there's more normal force at the bottom. And the reason for this, again, is that gravity is acting against us. Remember that at the top, gravity was helping out, and so the normal force was a little bit less. Okay, so that's a good example of how to set up these problems. You just have to be very careful about your positive and negative signs.